A final tool that will get used is something called the cumulative distribution function, which is quite a mouthful, so we will abbreviate it as a CDF. So the definition of a CDF looks somewhat complicated. In terms of a discrete function, the notation works like this. Now again, on the sheet, I've given you the formal definition, but this is how we write things out. The value of x that we are interested in ends up going here. What is the CDF? I like to think of it as a vacuum that adds up all the probability values for all the x values. For the two coin flips, if I were to write f of 0, in terms of the definition, this would say let y be all the values in your experiment that are less than or equal to 0, and then sum up the individual probability values. Well, in this particular case, there's only one outcome. X could either be 0, 1, or 2. There are no outcomes that are less than 0. So in this particular case, this adds up to the one single value where x is equal to 0. So the probability would be 1/4. Things become a little bit more useful in a CDF when we go up to the next case. So in terms of the notation, this would be a sum where y could be any of the values less than or equal to 1. So in our experiment, there are two such values. X is 0 and x is 1. And if I were to sum this up, I would get 3/4. Now, in this simple experiment, f of 2 would be the final value, and it would say sum up all of the probability outcomes when x is a number less than or equal to 2. Well, in our experiment, we would get these three values adding. And once you have covered all of the values of your random variable, you must always get to a sum of 1. That's one of the properties of your probability mass function, that everything has to sum up to 1. This basically says the vacuum cleaner has added up every possible outcome, and by the end of it, the vacuum cleaner must have sucked up all the probability. So the final thing that I want to mention is that you could represent a CDF with a graph, and this graph is always something that we call a step function. And in a similar way to what we did in the previous situation, we will have the values of x on the horizontal axis, and we will sum up the probabilities on the vertical. So the CDF could be represented as a piecewise function. We have no probability sucked up by our vacuum cleaner when we are less than 0. We suck up the probability for the first instance when this random variable is less than or equal to 0, or greater than or equal to 0, but strictly less than 1. So that means 1/4 here, 2, 3, and 4. So there would be 2/4, 3/4, and 1. We would have 3/4 when our value is including 1 but less than 2. And finally, we would have a 1 when our value goes to this case, and it would be 1 for anything greater than or equal to 3, where there really are no cases there. So in terms of a graph, we would have nothing going on here. There would be a circle popping up because as soon as you get to the outcome 0, there is some probability that your vacuum cleaner sucks up. And there are no outcomes between 0 and 1. As soon as you get to a 1, you have to have an open circle, and then your vacuum cleaner jumps up and has sucked up the probability in the next outcome, which was a half. And then once you get to 2, you've hit the final outcome, so your probability jumps up and it sucks up the final amount of probability that's left, and you just go from there. So this jump right here is the probability where x was 0. This jump right here was the probability that x was 1, and the jump right here was the probability that x was 2. So the CDF and the PMF give you two different ways of talking about the entire experiment. In discrete, we will be using the PMF almost exclusively, whereas when we get to continuous variables, the CDF will be of much more use.